Okay, so today we are going to be talking about convex optimization, in particular what is called as online convex optimization. So first, let's look at the reason why we even care about such a problem. So think about a data center that has like essentially as many servers as possible. So servers are not limited, as many servers as needed. Now demand is the number of requests made at time t. So let this be d of t. So d of t is the number of requests which are coming in at time t. All of them have to be serviced at time t itself. So any one server can meet or satisfy any number of demands, but while paying a convex cost essentially. So the cost is going to be some p of the number of requests or number of demands it satisfies, which is going to be a non-decreasing convex function. So at time t, let S of t be the number of servers which are active, number of servers that are active, and any I belongs to SIT satisfies Ri of t demands. So the constraint we have is that for I belong to S of t, Ri of t should be equal to d of t. So that is the number of demands being made, and the left hand side is the total number of demands being satisfied. So all of them to be satisfied, and the cost is going to be, cost is I belongs to S of t, P of Ri of t. So that's the cost to them. Now, if this is all there was, this problem is convex and you can solve it easily, right? Everybody sees that, right? That essentially if P function, and I'm not making P dependent on the server index, P is just some power function. So this is easy to solve. If you want to minimize this, RIT is going to be just essentially as small as possible because it's a convex cost. Now, in addition, an extra constraint is, which is where we really have to think about, that changing the number of active servers across time also incurs a cost. So that is a practical limitation. So S of t is the number of servers used at active at time t. So the cost really what we're going to call is switching cost. So switching is depending on how many new servers you're making active or inactive, you have to pay a cost, which we're going to call C of st comma C of S of t plus 1. And this again is an increasing function of the difference. So overall cost has two terms. One is the energy cost. So let's call this the energy cost or the power cost. So this is energy plus the switching cost, right? So in the long form, I belongs to S of t, P of Ri of t plus summation C of S of t, comma S of t plus 1. So this is summed over time also. So t equal to 1 to capital T. You want to minimize this with respect to choosing S of t. Is the problem clear?
Could you scroll up again? What was R of t?
So R of t is a variable. How many demands are met by the ith server which is active. So for I belongs to S of t, which is one among the active server, it satisfies Ri of t demands. And this is my satisfiability condition.
Okay.
That I have to satisfy all the demands. So summation Ri of t should be equal to dt.
Okay.
We can add it here. Subject to summation Ri of t for each time I belongs to S of t is equal to. So trade-off is clear, right? That if there was no switching cost, then once I get d of t, I could solve this convex program. That's not too difficult. But what I don't know is what's the, sorry, d of t. So d of t is revealed causally. So at time t, all the information you got is about the past. So you're going to make some choice about S of t and Ri of t. But this cost depends on what's going to happen in future also. That if you're using too few servers at particular time and the next time slot, a lot of demands show up, you'll have to pay a large cost in terms of the switching cost. And vice versa. If your currently S of t is very large and in the next slot the number of demands is very small, you are again going to make a lot of servers from active to inactive, and you're going to pay a large switching cost. So this is why this is an interesting online problem. And it's convex because of the convex nature of P we are going to choose. It is also called smooth for some reason, which will come to it. So this is essentially called smooth online convex optimization. Any questions? Okay, so now we're going to write the same. So this is the motivation to consider this problem. We're going to look at a more abstract form of this problem, for which this is a special case. So let at time t, so time is discrete, a convex function f of t, which is map from Rn to R plus, is revealed. Okay, that's what is happening over at each point of time. Decision to pick xk, sorry, xt at each time t, this decision you have to make belonging to Rn, such that there are two costs, such that the sum of following two costs are minimized. F of xt minus ft of xt star. So this is one type of cost. The other type of cost is, so this is the suboptimality cost, where xt star is R minimum ft of x. Okay, and the second type of cost is the moment cost, which is C of xt comma xt minus 1. So for example, we are going to look at this particular function. So, okay, so this is going to be my what we call as hitting cost ht, and this is going to be the moment cost mt. So the sum of the total cost ct is summation t going from 1 to capital T. So this is not ct. The total cost is ht plus mt. So it's much easier to understand this in the abstract form. So what are we getting? At each time t, we're getting a convex function for ourselves. That convex function has an optimizer which is defined to be xt star. In the past, you have chosen certain locations. So x1, x2 up to xt minus 1, you already chosen. The decision at time t is only going to depend on what you have chosen at time t minus 1 via the moment cost. That how much movement you are going to make from xt minus 1 over here to xt. See, you would ideally like to go to xt star, but this movement cost is going to prevent you from moving all the way to the optimal point. So the overall cost is going to be ht plus mt, and minimize this with respect to x of t. Is the problem clear?
Yes.
Yes.
Any comments on the problem? So initial location x0 is 0 without loss of generality. Hari, is this clear? The problem is clear?
Yes.
That what trade-offs there are, it should be obvious right now. That if I pick an xt which is very close to xt star, the hitting cost is going to be very small, but possibly my movement cost is going to be large. And because I'm adding the two together, I would like to have a compromise between the two. Okay, so we're going to make one assumption to make this somewhat easier for ourselves, that all ft is essentially each ft, each convex function t revealed is assumed to be m strongly convex. Which, what does it mean? That del ftx minus del fty transpose x minus y is greater than m times x minus y. And all the norms I'm going to write are all two norms. So this is what this means by each ft being m strongly convex. And so now we would like to write a guarantee for an algorithm in terms of m while independent of the dimension of the problem. So dimension of the problem is n. So we are working over n dimensional space. The strongly convex parameter is m, and our objective for the moment is to get an algorithm whose competitive ratio possibly will depend only on m but not on n. Okay, so suppose you're faced with this problem, what you would like to do? Any algorithm which comes to mind? You can not worry about the strong convexity of it. This is all you want to solve. You are currently standing at point xt minus 1. A new function is presented to you, and you know what kind of cost you're going to incur. If you think about it, this is not very different from the facility location problem, for example. Any ideas? You've seen these kind of things already in the course.
So like if we compare it with the facility location problem,
Yeah,
it is more like either you pick a new facility or not, but this is more continuous version of it.
that's okay. But after all, opening a new facility only costed you something, and not opening a facility also costed you something. So there are essentially two discrete costs. Similarly, we are getting something similar here. There is, if I move very close to xt star, my hitting cost will be small, and if I stay close to where I am, my movement cost will be small.
We look at the line joining your current position and xt star,
Okay.
and then choose the point at which the sum is minimum.
All right. So that's a reasonable algorithm. So suppose you are currently at xt minus 1. For, let's say, this is somewhat. So this is whole space Rn, and for ft, let this be my xt star. So you connected the line. So this is weird, but just think about, imagine that this is what I'm doing is okay. Okay, so at this, as I move closer to xt star, my hitting cost is going down. So hitting cost is going down this way, while the movement cost is going down this way, right? So as I stay closer and closer to xt minus 1, my movement cost is going to be small, while the hitting cost keeps getting smaller as I move towards xt star. So what Pranchu is suggesting is pick a point at which mt is equal to ht. Correct? That's your algorithm. Pick
Yes.
xt such
Yes.
that mt is equal to ht. So it's a reasonable algorithm. I don't know how to analyze this. We will look at a very similar, like a variant of this, which can be analyzed. So the idea is not very different. It's just that this doesn't pick exactly where mt is equal to ht. We're going to pick something in slightly more using the properties that f is convex. See, this algorithm might have, like, I don't know how nicely one can analyze this when ft is convex. So we'll try to extract some convexity properties of ft and try to do something very similar. So ballpark, this is what we want to do. We're not going to do exactly this, but a variation of this. Okay. So now, so what this algorithm Pranchu suggested is essentially equalizing the movement cost and the hitting cost. So algorithm name is called online balance DC. So let me define it via using a level set of function ft. So I'm not going to write over and over that function ft, all ft's are m smoothly convex is lt of l. So level is little l. So all x belongs to Rn such that ft of x is less than equal to. So in one dimension, if you, this is your L, this is the area, is what LTL is. And we know that LTL is convex since ft is convex. So things are nice because I'm in a good shape because functions ft are convex. Okay. So now what would you like? So suppose this is my point xt star, and I can draw these contour maps around it. So call this level 1, level 2, level. So this is L is equal to some 3, for example. Makes sense, right? That for this is for a particular function ft. These are my contour maps. So for at this value f of x. Okay, so I think I missed something that throughout. It's not a really an assumption that xt star is equal to 0 for all ft. This is actually the worst for a non-linear algorithm. So without loss of generality, we are going to assume that the minimizers for all these convex functions is actually 0. So that is why I can do this, that fx is less than equal to 3, fx, ftx is less than equal to 2, ftx is less than. Is this clear what I'm drawing here? So this is my xt star, at which point ft of xt star is equal to 0. Okay. And now I'm somewhere at xt minus 1. So what I want to do is pick a level L. Okay, so pick a level L, and that will define my level set LT of L, and find a point xt, which is R min of x minus xt minus 1 square, where x belongs to LTL. Can somebody interpret what I'm trying to do here? That suppose I'm trying to find my point xt using this formula. First of all, is this clear what is written here? That I'm concentrating my attention to all points which belong to a particular level set LT of L. And among those x, I'm trying to find the point which is closest to xt minus 1. So what are the implications of such an approach? Is the algorithm clear?
Yes. It
Yes.
puts
So
an upper bound on the.
it is controlling hitting cost to be at most L,
Yeah.
and under this constraint, minimizing the movement cost. That is what essentially is going on. Because X belongs to LT, L is only the feasible set, so hitting cost is at most L. And under this constraint, trying to minimize it. So this online balance descent is exactly going to do this. But now, how to choose L is the question. What L you are happy with? Because as L changes, everything changes, right? So this particular algorithm is going to do the following. So I'm going to define a projection operator. So this is my projection operator. Projecting X onto, so my level set is some convex set. This is my X and is going to project it. So this is my projection operator. This is LTF. This is the, all right. So this should not be R. So this is just the projection. Oh, sorry, R is correct. So I want the point which it doesn't. Fine. So now here is an algorithm. So at time t, let the previous location be xt minus 1 and the new function is ft. Then define x of L to be the projection of LT of L of xt minus 1. I'm yet to choose L, okay? Yet to choose L. So for any little L, this is my x of L definition. So this is my definition of x of L. What exactly I'm going to do? Doing follow. On arrival of a new function ft, initialize L is equal to ft of xt star, which in our current case is going to be 0, because we are assuming that the optimal point, the value is 0. Iteratively increase L until either of the two conditions are met. One, x of L is equal to xt star, or and 1/2 of x of L minus xt minus 1 whole square for some beta greater than 0, or 2 1/2 of x of L minus xt minus 1 whole square. So in either of the two conditions, you terminate. And remember the definition of x of L. X of L is nothing but the projection of, so you get the current value of L that defines your level set, and you take the projection of your previous location onto this level set and call that x of L. So to begin with, L is a point which is equal to 0. So I don't want to move at all from my optimal point. Possibly I cannot satisfy either of the two conditions. Then I keep changing L until I hit either of the two conditions. First condition is interesting, that x of L is nothing but the xt star. At the same time, I'm not too far away from my original point. See, x of L is my new location essentially, and xt minus 1 is the previous location. So this is okay. This is great that my hitting cost is 0, but my movement cost should not be too large. Or otherwise, I will just stop as soon as my movement cost is equal to beta times the hitting cost. So why is L the hitting cost? I claim that L is the hitting cost. just because of the fact that we have taken ft of xt star is equal to 0. So hitting cost is nothing but ft of xt minus ft of xt star is equal to ftxt, and which is by definition equal to L. Correct? Is everybody okay with the final remark?
I have a question.
Yes?
So when L is 0, are we so L is ft of xt star. So it is the value point of the next
Function.
function.
So I'm taking L equal to 0. So that is, I'm not deviating at all. So if you look at my contour functions, I'm just sticking here. I'm not moving at all. Can you see this? That ft of xt star is equal to 0. So the contour map here is exactly a single point. So that is where I'm beginning. So I am not giving you any slack. So xt minus 1 will directly get projected to xt star only. That's the only convex point. So if you do that, but I will be happy if doing this, my movement cost is not too large compared to L. So that cannot be satisfied for L equal to 0 unless both these points are the same over here.
Okay.
Does that satisfy?
Yeah. Okay.
Yeah. So L equal to 0 is unlikely to be satisfied unless x of L is equal to xt minus 1 itself. So you will actually start increasing L. At some point, either one of the two conditions, eventually it will, as you keep increasing L further and further, eventually somewhere this will happen, no doubt. At that point, I will stop and declare that I am done. So stop as soon as either of the two conditions are met. And let LF be the stopping or value of L at termination. Then your x of t is nothing but how much? X of LF, which is the projection of LT LT of LF of xt minus. That's your new one. Is everybody clear with the algorithm? It's very simple. It's just building upon. So it starts with the actual point xt star. If you can match the condition, you stop. Otherwise, you keep increasing L. So your convex set of interest keeps increasing. So suppose at L equal to 1, you are able to find that either of the two conditions met. So you're at somewhere belonging to this region is where xt minus 1 is projected down. So the hitting cost is something which is at most 1, while the movement cost is from here all the way to some point in this region. Kumar, is this clear?
Yes.
I feel hesitancy, so you want some clarification? If you want any clarification at this point, I'll be told.
I mean, this is also doing the same thing what Pansu
It's
suggested.
not same. That's the only point. It's not making it equal. It's only looking to go as far as some beta fraction of it.
And this is like numerical implementation, something like that.
Not really. So you will eventually figure out that if you want to make it exactly equal, you might face some trouble. So we'll see what values of beta this algorithm can give you something. So it won't be that for all values of beta we'll be able to say something. Possibly. In spirit, I completely agree that that is precisely what is going on. But there are some nuances. Possibly we cannot get a guarantee. We'll have to eventually choose beta in terms of the convexity parameter M to get something interesting. Okay. So now I have my hitting costs and movement cost. The same thing for OPT will be denoted as HT, OPT and empty OPT. And one fact you should remember, what we already discussed, is that because we are taking ft of xt star is equal to 0, then for our algorithm, mt is at most beta times ht. For certain cases, it will be exactly equal, which will be used in the proof. But in either, like throughout, is at most beta times ht. Okay, so here is the theorem. Algorithm OBD has a competitive ratio of 3 plus order 1 by m with beta is equal to 2 plus 10 by m. That is why I said we'll have to choose a particular value of beta. And remark that this is independent of the underlying dimension of the functions. Underlying dimension. Okay. Proof. So one final time, we are going to again look at a potential function argument. So by now, either you're bored or you are fascinated. I don't know which state you are in. I am always fascinated by the potential function arguments because every time you need something new. Okay. So it's a two variable argument defined to be.
What is this M?
M is the strong convexity parameter for all functions ft.
And N is the dimension of X.
So let me just say again. So this is my function space, and M is the strong convexity parameter for all ft's. Okay. So some eta greater than 0. All right. So this dimension we will look for the algorithm, and this will be for the OPT. You can think of this as some sort of difference of the movement cost, or how far you are compared to the OPT. That's what this is capturing. Eta is some constant to be greater than 0. So initially, both the algorithm and the OPT starts at the same point, which is x0. So phi of x0 x0 OPT is equal to 0. So that's an important thing to remember because both of them start at the same time. And phi of xt OPT is always greater than 0 because of the definition. All right. So there are some simple geometric lemmas. So let A, B, and C belong to Rn, and if angle theta between vectors A minus C and B minus C belongs to lies in pi by 2 to 3 pi by 2, then phi of A comma C minus phi of A comma B is less than equal to minus of phi B comma C. So these are elementary. I'm not going to prove today. You can, if you want to see the proof, you can see the notes. And one more such lemma. So for A, B, C belongs to Rn. So let this call lemma 1 and lemma 2. Phi of A
What is
comma
the role of eta in this potential?
yeah, so eta will play a role. Eventually, we'll have to pick a eta to claim the guarantee, as we have done before. So we always have a constant in the front, and then we choose the constant to make everything work. We have done this in speed scaling. It's very similar to that. So again, this is an elementary. You use cosine's law. So there's nothing to be done here. Just use elementary ideas and prove it. Okay. So now comes the first main result. So let's call them propositions. So lemma 3. Let xt and xtopt be the location chosen by OBD and OPT respectively. Then for each t, and phi of xt comma xtopt is less than equal to 4 eta by m ht minus 4 eta by m HTOPT. HT is the hitting cost, HTOPT is the hitting cost of the OPT. Okay, so can somebody help me prove this? It's actually again, it's an elementary proof. So by definition, what is phi of xt comma xtopt? This is nothing but eta times xt minus xtopt. So maybe I'll write something and then you can tell me why this is well defined. So can somebody justify equation number A? I've only introduced xt star inside, that's all. So here is xt star, here is xt star. Xt and xtopt as before.
Triangle inequality.
Yeah, so you're slightly hesitant, but yes, that is correct. So if you just use triangle inequality and the fact that where xt star, remember, is the optimizer of xt. Okay, so now we can expand this. What will we get? We'll get xt minus xt star square plus xtopt minus xt star square plus 2 times xt minus xt star xtopt minus xt star. So if I wanted a bound only in terms of these and these terms, what can I do here? Can somebody tell me the simplest thing I can do? So I have a product term here and here, but I only want in terms of these guys as additive terms. AMGM inequality. So this will be 2 times xt minus xt star square plus 2 times xtopt minus xt star. So this is just AMGM. And now, what does strong convexity tell us about these two things in terms of HT? So what is HT first of all? HT is nothing but FT of XT. Similarly, HTOPT is FT of XTOPT because we are taking XT star is equal to 0, right? So now what does strong convexity tell us to connect these two things here and here? Do you want me to remind a definition of strong convexity?
We get a bound on del of f of
Oh, del is important. So check it yourself, you can get this. So 2 is as it is. What you get is that is less than equal to 2 times ftx ft xt by m, and similarly 2 times ft xt opt. You can check this from whatever property I wrote down. So this is at most 4 eta ht by m plus 4 eta ht opt by. Any questions? So the way I wrote the strong convexity property was in terms of dels, but you can deduce what I wrote from this. So what I wrote was ft by square is, sorry, is greater than n times x minus. It's an elementary property what I'm using. So if you just see this, or you want to, what I'm claiming is that xt minus xt star is less than equal to 2 times ft of xt. So this follows this. Okay, so we are essentially done. Kumar, Hari, any questions? So most of the claims you are going to make are very elementary, directly using the definition. So now what do you want to do? So earlier, if you remember our speed scaling ideas, what did we do? We tried to say we had a function phi of t and we wanted to compute the running cost, which was p of s of t plus phi of t, and compare this with some constant times the running cost of the OPT. There was an integral, now this is a summation, so there is not really any difference as such. So now what we want to do is we want to control the running cost. So running cost is ht plus mt for us, right? The hitting cost at time t, the movement cost at time t plus del phi. This is what we want to control. Del is now a difference. So there we had d by dt. Now we have a difference. So what we really want to control is how large is this quantity. So case 1, which will be an easy case, where ht is less than equal to ht opt. So how much is del phi t? I should write here. Is by definition xt opt minus phi xt minus 1 xt minus 1. That's just by definition. Phi t minus 1. And this we know is at most xt opt. And by our previous lemma, we just get that this is at most 4 eta by m ht. ht plus 4 eta by m ht. So no, nothing fancy really, very simple. So therefore ht plus mt plus del phi t is at most ht plus mt plus 4 eta by m ht plus 4 eta by m ht opt. Now we know because of this our condition we have started, ht is at most ht opt. So I can make this guy ht opt. And if you remember, we said something about the relationship between mt and ht. Does anybody remember? How large is mt in terms of ht for OBD?
Beta times ht.
Right. So this is a fact. So combining these two together, putting ht opt on the side. So all terms are now in terms of ht opt because ht is at most h opt. Mt I'm able to write in terms of ht. So 1 plus beta plus 8 eta over m h opt. Okay, so this tells us that ht plus mt plus del phi t. Now how do I claim that summation ht plus mt is less than something? See, this is my running cost, right? And this is my overall cost. I would like to bound this with respect to the OPT's cost somehow. So how do I do that? So this is at most t equal to 1 to capital T ht plus mt plus del phi of t. Why is this true? Because del phi of t is almost, is it always greater than equal to 0? Phi t is greater than equal to 0 for it, but is it that del phi of t is greater than 0? Question is summation t going from 1 to capital T del phi t greater than equal to 0. What do we know? That phi of t is greater than 0 for all t. That's all we know. But if you expand this, what will you get? You will get the first term and the last term. So the last term will be phi of x capital T opt minus phi of x0 opt. That is exactly equal to this. Is everybody with me? See,
Yes.
all the other terms will cancel off because of the way del phi t is defined. Del phi t is nothing but phi t minus 1. So the first and the last term will survive. So now why is this whole term greater than equal to 0? Why is this minus this greater than equal to 0?
Second term is 0 and first term is non-negative.
Correct. So that is why we have that summation phi t is greater than 0. So this inequality is true. Okay. So now we're going to just use the bound we have already got for ourselves from here. So this tells us that this is at most t going from 1 to capital T 1 plus beta plus 8 eta over m h t opt. And this by definition it is 1 plus beta 8 eta by m COPT. See, COPT has two parts. One is HTOPT plus MTOPT. We don't have an MTOPT contribution, so this is at most COPT. So the competitive ratio in this case, how much are we able to get? This is 1 plus beta plus 8 eta over m. So this is the simple case. Now we'll worry about the difficult case. So case 2, where the hitting cost of the algorithm is actually larger than HTOPT. So this is where really the properties of the algorithm will be used. So far so good? Three? Things are okay?
Yeah.
Okay. So now what does this mean that HT is strictly greater than HOPT? Can you give me a simple argument to this fact that this is my XT minus 1. This is my level set L of LT of LF. Remember LF is the terminating level. This is XT minus 1. Somewhere this is XT star. And the projection will be on the boundary. Let's call this XT. Correct? XT star is inside. And where is XT OPT? That's the question. If HT is greater than HOPT, where is XT OPT with respect to XT? So what is HT? HT is FT of XT. What is HT OPT? FT of XT OPT. The condition we are under is HT is strictly larger than HT OPT. So where is this point XT OPT in this figure? Is it outside or is it inside?
Inside is in a smaller level set.
Correct. So that is why this is strictly inside. Kumar, is this clear? This is important.
Yes.
So because of the condition that HT-OPT is strictly smaller than HT, I know that XT is strictly inside this convex set. It's not on the boundary. So now what do I know about the geometry of this? What is the angle made between? Okay, so let me try to make it slightly easier for all of us. So, okay, so what is this angle? Theta.
Obtuse because of convexity.
Right. So not only just because of convexity, also because of this condition. Obtuse because of Ft being convex which implies that LT LF is convex, and the fact that XTOPT belongs to the interior of LTLF. So everything put together tells us that this angle theta is obtuse. Hari, is this okay?
Yeah.
And now you can potentially look back at why we did those two propositions, which are elementary. So this is the I wanted to look at angle between two particular vectors which are obtuse, and this lemma is what I'm going to use later. So that is why these lemmas are useful. So the main property used for the moment is that XTOPT lies to the interior, and this angle made between XT minus 1 minus XT and XT minus XTOPT is an obtuse angle. Okay, so now let's again do the similar exercise. How much is del phi? So just to repeat myself here, minus phi of XT minus 1. So I'm going to add and subtract quantity, which is phi of XT minus 1, comma XTOPT plus phi of XT minus 1, comma XTOPT minus the original term, XT minus 1, comma XT minus 1. So this and this is identical. And now I claim that this is at most phi of XT, comma XT minus 1. Okay. And now I'm going to combine this. So let's write a minus here, minus here. So on this negative sign, I'm going to put 2 times phi xt opt xt minus 1 opt and plus phi of xt minus 1 xt minus 1. Let me check if I'm not making a mistake here. So this is application of my proposition of elementary propositions on the first 1, 2, 3 terms. That's all I have done. Okay. Any questions at this point? So remember, what was the angle I was looking at? I was looking at the angle between this vector, which is xt minus 1 and xt, and this vector, which is xt opt and xt. So that is where I'm actually applying this lemmas. Do you want me to recollect those lemmas or other propositions? So what did we say here? That suppose vectors a minus c and b minus c make an obtuse angle, then phi of a comma c minus phi of a comma b is at most minus of phi of b comma c. So that is what I am applying on the first 2 terms. And for any ABC, I know that phi of AC minus phi of AB is at most 2 times phi BC plus phi AB. So that is being applied twice to get our current set of equations. All right. So now tell me something more. So for the OBD algorithm, how much is phi of xt comma xt minus 1 is equal to? Eta times how much? The people forgotten definition of phi. Phi is xy eta x minus y whole square. Right? So between xt and xt minus 1, the difference is exactly the moment cost. So I can write this. Similarly, phi of xt opt, xt minus 1 opt is equal to eta times mt opt.
Would it be 2 eta times mt?
Yeah, I also thought so. For the moment, yeah, let's not worry about 2.
Okay.
It could be that 2 is needed, or I have made a mistake somewhere. So yeah, up to 2, these two things are okay. Because I think we have defined movement cost to be half x minus y whole square, while in my phi I have defined it, so it should be 2. So let me check in my notes where I have made a mistake. But yeah, up to 2 things are okay. Okay, so now using this and this back over here, what do we get? That delta phi of t is minus eta mt plus 2 eta mt opt and plus phi of xt minus 1 comma xt minus 1. So we are almost done now. So now let's try to do something very similar to before, that ht plus mt plus del phi of t. This is at most ht plus mt minus eta mt plus 2 eta mt plus phi of xt minus 1 comma xt minus 1. Okay, so now what was our relationship between ht and mt?
ht less than equal to b time.
Right. Can you make it tight? When is it tight? See, there are two conditions algorithm stops. One is that, can somebody wants to remind me? So that x of L is x star t. That's and 1/2 xl minus xt minus 1 is less than beta times L. Or otherwise it is half xl minus xt minus 1 square here is equal to beta. So which condition are we in? Is it possible that we are in this while ht, see we are under the condition that ht is strictly greater than hopt, correct? That's the case we are interested in. So when this is true, which of the two have to be necessarily true? Is it possible that condition 1 is true? Can this be true? When ht is greater than hopt. Hari, are you getting lost in definitions?
Yeah, yeah.
So ask me, ht is what? Ht is ft of xt. What is ht opt? Is ft of xt opt. We are in the case when this is strictly greater than 0. This is the case we have for ourselves. Now we are claiming under this case, is it possible that x of L, which is nothing but xt, can it be xt star?
No,
So
it
is
is
it
not
possible?
in that
Sorry,
point yet.
that xt, which is equal to x of L, is equal to xt star. Is it possible given that it is strictly larger than ft xt opt? See, this is a positive quantity. So this is strictly greater than 0. And we know that at xt star, ft of xt star is equal to 0. So this cannot be true. So we cannot be in case number 1. So necessarily we are in case number 2, which means that ht is in fact equal to beta times mt. So I need this. I am not, it will not be sufficient to look at the inequality anymore because we are going in a different direction. So here I want to replace the minus here of mt by beta ht. So that is why I need equality, not less than equal. Is everybody okay with this? That why do we have ht is equal to beta mt in this case? Kumar?
Yes.
It should be obvious. I don't want anybody to be unclear. So ask me if you're getting lost in somewhere. Is everybody comfortable? Then we can move ahead.
Yes.
Yes.
Okay. Okay. So now we're just going to use this inequality in what you see. Important thing is it's not a positive sign with empty I'm worried about. I'm worried about the negative sign. Because of the negative sign, I cannot work with less than equal to. I have to have strict equality. So then I can write the above inequality ht plus mt plus del phi of t to be less than equal to 1 plus 1 by beta minus eta times mt plus 2 times eta mt opt. Did I forget to write something here? There was one more term here. So minus mt, this is mt. So 2 times eta opt. And what do I do with this term? This I've already upper bounded my lemma in terms of 4 eta by m ht minus 1 plus 4 eta by m ht minus 1 opt. So I've just gone one step back. Everything now over here is for step t minus 1. So I can use the same lemma I derived earlier with index being ht minus 1. Okay, so now we're going to choose finally the value of eta to be 1 plus 1 by beta, which will give us that ht plus mt plus del phi t is at most essentially just to cancel this term off. 2 eta mt opt plus 4 eta by m ht minus 1 plus 4 eta by m ht minus 1. Okay, so now can somebody complete the proof? How do I combine this now? So remember my total cost is just summation of this, which is at most, this we have already seen. And this from our inequality above is at most equal to 1 to capital P 4 eta by m times HTOPT. I'm just replacing t with t minus 1. Going from 1 to capital T eta MTOPT and plus going from 1 to capital T 4 eta by m HT minus 1. So this one should be called HT. So how much is this term plus this term? They are both OPT terms. So I can always say that this is at most max of 4 eta by m comma 2 eta COPT. Everybody is happy with that, I guess. The only term I'm left to do is to take care of this term 4 eta by m, and this term corresponds to the algorithm itself. Okay, so now how do I take, so this is my COBD, right? I want to write this in terms of COBD. Can somebody help me? And the hint is that use this fact that MT is equal to beta times HT. Using this, can you write the last term in terms of COBD times some constants?
COBD is equal to 1 plus beta times HT.
COBD
MT plus HT, so 1 plus beta times
is
HT.
1 plus beta times how much?
HT.
Okay, so if I use that, what will I get? I will simply replace this to be max of, see this is again very important, and this is true only when we are in this case 2. Otherwise there is only an inequality which doesn't help us. COPT plus 4 eta by m times COBD by 1 plus beta. This is what we get. So finally, remember our choice is eta to be greater than 1 plus 1 by beta, and you make another choice of beta to be 2 plus 10 by m. You can, so now you can move this guy over here because they're common terms. So you get the competitive ratio of OBD to be at most max of 4 eta by m comma 2 eta. We'll get few more terms actually because of the things moving around. So let me not write that. All you can say is that once you do this, is going to be 3 plus 1 by. So some algebra is needed to move these guys around and take. All right, so that is what we have. So the proof is kind of elementary. Algorithm is kind of intuitive. It's not exactly what Brancho suggested, but it's not very far away from that. And the main idea is that you keep finding level sets, keep increasing their sizes as long as you can satisfy one of the two conditions, and then you stop. Any questions?
So compared to, so you discussed one setup before coming to this abstract form.
Yes.
So I mean, there is one difference that I see. So in the problem that you discussed, so if I have more number of open servers,
Yeah.
then if demand suddenly decreases, then I don't decrease the number of.
You do, right? So that problem is just a one-dimensional problem for this. So n is equal to 1, you will get that problem. That think of this working on a line that you are currently at xt minus 1. You choose xt here or here. Both sides you are going to pay a penalty. So if you decrease it or you increase it, both sides are going to pay a penalty. So
No,
FT,
but why will I decrease the load? I mean, if new demand is coming, I will keep it. If I have more servers operating, I will give it to the
but
I
there
will
is
not decrease the number of servers because other cost that is a function of number of jobs being processed at a server. So that is kind of increasing.
no. So maybe I missed something, but suppose the demand has decreased, right? And you're still operating all the active servers. There is a operational cost for those servers that is reflected by f of t. So suppose 10 servers are working at time 1. Now 2 servers are working at time 2. Yours or 2 servers are need. So okay, let's do this. Okay, so what is your example? Let's suppose 10 demands came at time 1 and 2 demands are going to come at time 2. What is your objection? So at time 1, how many will you operate? You'll operate certain number of servers. Correct? So number of servers operated at time 1, let be S1. Now with respect to S1, there is an operational cost. And that also depends on 10 and the particular cost functions you're going to work with. Correct?
Yes.
Now at time 2, how many servers will you operate? If you keep it identical to before, you're unnecessarily paying a price of all the active servers.
I mean, I thought this f was increasing function of RIT. So if RI is 0, then
what does RI 0 means?
I mean, no job is being I have 3 extra servers that are running, but no jobs.
Yeah, so then you can think increasing function of the following type will solve your misery. F of x is equal to x power alpha plus beta. Takes care of your problems?
Yes.
Oh, so is this not an increasing function?
Yeah.
So idling servers before, so switching is a problem. Problem is switching, that switching from active to inactive state costs of energy. So if you want to keep it active, you still have to pay a certain price. So if it is just x power alpha, then it's a different problem. Then you can do what you want to do. But keeping them idling while being active also costs energy. Does that resolve the problem?
Yes.